Hi everybody. I had a couple of students ask me about work session 18, question 10. So we're going to consider the reaction of iodine reacting with chlorine to make iodine chloride, and we're provided the equilibrium constant 81.9 at 25 degrees Celsius. And we are asked to calculate delta G of the reaction for the following conditions. So we'll calculate it for standard conditions, we'll determine it for equilibrium, and we'll determine it under these non-standard conditions. All right, so when we want to calculate delta G under standard conditions using the equilibrium constant, the formula we would use, and this is on your information sheet, is delta G of the reaction is equal to negative RT natural log of K. And when you're working with these types of problems, when you need to calculate for Gibbs free energy, which is an energy unit, the R constant you will use is 8.314 joules per moles Kelvin. And if you're taking my class, that is provided on the conversion factor sheet. That has different equalities and constants that are useful for general chemistry. So that's the one you would want to use, and it's important to recognize that because a lot of times Gibbs free energy is given in kilojoules. So when we calculate it though, if you're using that R constant, then your answer would be in joules and you'll need to convert it into kilojoules later. Also, temperature needs to be in Kelvin, and so this says that we are at 25 degrees Celsius, so we're going to add 273. So 25 plus 273 is equal to 298. Now you may go out to the hundredths place, and that would be 298.15. And then you might have some rounding error if you decide to use 298 instead of doing 298.15. And the way you would determine that is how many significant figures that you're looking for this specific type of problem. So for my class, 3 is enough since I teach second semester of general chemistry, but if you're taking a physics class, you may want more significant figures. All right, so we're going to plug that in. So negative 8.314 joules per mole Kelvin. I always like to write the units just to remind myself it's in joules, it's not in kilojoules. And then times 298 Kelvin times natural log of 81.9. And when I solve for that, I get a negative 10,000. And I'm rounding already, negative 10,900 joules. I divide by a 1,000 to get in kilojoules, so negative 10.9 kilojoules. All right, then we're asked to calculate, well, what is Gibbs free energy at equilibrium? Well, we know from chapter 15, if you're taking my course, since chapter 15, we recognize that equilibrium is when K is equal to 1. And what is the natural log of 1? It's 0. So that's how I remember if we're at equilibrium where K is equal to 1, then the Gibbs free energy is equal to 0. Another way to remember that conceptually, if you are at equilibrium, and we looked at a graph together in my lectures if you watched them, the graph looks something like this where we're at the bottom of the well and that's when we reached equilibrium. If we were higher up on the left side, then we were favoring reactants. If we were up higher on the right side, then we were favoring products. But once we reach equilibrium, we're like the bottom of the well here, right? That means the reaction is not going forward, nor is it going backwards. It's just kind of right there, equilibrium. It's hit the sweet spot there. And so that means that no more work is needed to be done. So that's the reason why Gibbs free energy is 0. So no more work needs to be done. We're not going forwards, we're not going backwards, we're already at equilibrium. So conceptually, you can think of it that way. Or like I said, when I was a student, I used a lot of algebra to remember trends and relationships. And so for me, I was like, well, I know equilibrium is when K is 1. So if I were to plug that into this formula here, that means delta G is 0 at equilibrium. All right. I also taught you that you can calculate Gibbs free energy at non-standard conditions. So in this case, we can see that the partial pressures of our reactants and products are not 1 atmosphere, which indicates I'll need to calculate Q for the non-standard conditions. And the equation for that is delta G of the reaction is equal to delta G of the reaction plus RT natural log of Q. And so we're going to use this one here that we calculated for when K was 81.9 at 25 degrees Celsius. That will go in here. And we will use these values here to calculate for Q, the reaction quotient. We've been talking about the reaction quotient ever since, ever since chapter 15, right, when we did equilibrium, products over reactants. And because we're given impartial pressures, we're good. We can do QP. That little P stands for we're working with pressures. If you were working with concentrations, then that's when you talk about KC or QC. So if you're reviewing over that chapter 15 material to prepare for your final exam, just make sure you understand like what, KP versus KC, QP versus QC. You always want to make sure you're comparing the same type of equilibrium constant and reaction quotient. So we're working in partial pressure, so we're good. We're in the appropriate units, no need to do any conversions between KC and KP. So Q is equal to products over reactants. So the iodine chloride squared, because the stoichiometric coefficient is 2, over iodine times the chlorine. And then we can plug in our partial pressures, and I got 90.5325. So I kept a few digits there. And we have delta G, we had negative 10.9 kilojoules plus, remember R is in joules, so in this case here, maybe you want to convert R into kilojoules so everything is consistent, so that would be 8.314 times 10 to the negative third times 298. Once again, if you do 298.15, you'll get a slightly different answer, and then times the natural log of Q, which is the 90.53. Let me go ahead and move this somewhere else. So 0.5325. And when we plug that in, you should get 0.263 kilojoules under these conditions. All right. So when you're studying for this particular chapter, there are several equations to use. If you're taking my class, they're provided on the info sheet, so be sure to feel comfortable finding the equation that you'll need to use to calculate under different conditions. In addition, make sure that you're using the appropriate units. A lot of times I've noticed students will use R as joules and then maybe plug in kilojoules for that Gibbs free energy, and when the units are not consistent, that's when errors occur. Don't forget you have to work in Kelvin always. Usually you provide the temperature in Celsius because that's what our thermometers work in, but a lot of these equations we're working in Kelvin. That's how they were derived originally. Also, a good trick to remember here is that at equilibrium, Gibbs free energy is 0. There's no more work that needs to be done. We're already at our dynamic equilibrium. And I think that's about it. So like I said, when you're practicing problems and you're using a certain equation, just make sure that you can identify, okay, I use delta G is equal to negative RT natural log of the equilibrium constant K under standard conditions, and I was provided K. So but then I had to use delta G is equal to delta G's with a degree symbol, standard plus RT natural log Q. And then that's when you would need to use that equation when you're given partial pressures maybe, or maybe you're given different concentrations other than 1 molar. That's indicating you're not at standard conditions. I hope me going over this question helps you out. If you have any more questions, don't hesitate to email me. Good luck studying.